All right, so the front of this warm-up is just some practice using the different calculator commands. So for each one, it says basically sketch a little picture, put in the calculator command, and then what is the result? So the first one says, what percent of scores fall below a z-score of negative 0.7? So again, if you've got your little curve there, this part is 0. All right, the peak of the curve is always at 0. -1 is where the curve sort of switches direction from concave down to concave up. So it's like an inflection point. So negative 0.7 would be right about here. So we're basically looking for this section of the curve. And again, this is just useful to sort of give you a visual guide so that when you put the numbers into the calculator, you have some concept of whether the answer it spits out is correct or incorrect. So as far as what we'd put into the calculator, we'd be using NCDF from negative 9999 because we're going below up to positive, not positive, up to negative 0.7 with a mean of 0 and a standard deviation of 1. And again, for us, that mean and standard deviation is always going to be 0 and 1 all through this unit. All right, so it's just going to NCDF. Negative 9999 to negative 0.7. 0 and 1 can stay the same. That gives us 24.2420 when we round it, which is 24.20%. 30% of scores fall below what z-score? All right, so this question's a little different. All right, this question is telling you that 30% of the curve is shaded, and they want to know what does that correspond to? All right, what z-score is that? Versus this one was telling you the z-score, it was telling you it was negative 0.7, and then the question was, what percentage does that equal? So there's two different questions we can ask here. So when we're trying to find the z-score, that's where we're going to use inverse norm. All right, so we're basically saying what z-score corresponds to the 30th percentile when the mean is 0 and when the standard deviation is 1. All right, so that's in the same exact menu. The area would be 0.3, the mean would be 0, the standard deviation would be 1. And that's not a percentage there, that's a z-score. So negative 0.5244. And just a reminder that this one is not a percent, this one is a z-score. All right, so that's referring to basically half a standard deviation below the mean. All right, what percent of scores fall above a z-score of 0.25? All right, so again, if we've got our curve, there's 0. So 0.25 might be right about there. And then the question we're asking is, how much shading does that give us? All right, so we're doing an NCDF from 0.25 to 9999 when the mean is 0 and the standard deviation is 1. All right, so again, we would just go right back here. 0.25 is our lower bound, positive 999 is our upper bound, 0 and 1 stays the same. And again, this time we are getting a percentage, so that's 0.4013 or 40.13%. Now again, I don't actually require you to switch it over to a percent. You can just leave your answer as 0.4013. Using a normal model, 100, 14, what percent of scores fall below 108? So remember, this right here is our mean. This right here is our standard deviation. Now, in this unit, the way I'm requiring you to do these problems is to convert this to a z-score. All right, so we would say that z equals 108 minus 100 divided by 14, which basically means we're doing 8 divided by 14. And that works out to 0.5714. So what this is asking us, if we go back to our curve here, we've got a z-score of 0.5714, which might be about right here. Again, these are just rough estimates, and it's saying what area is below that. So I should be expecting to get an answer above 50% when I do this. All right, so let's see what we actually get. So we're doing an NCDF from negative 9999 to positive 5714. When the mean is 0, the standard deviation is 1. Again, if we go back here, negative 9999, positive 0.5714, mean of 0, standard deviation of 1. And I am getting something above 50%. I'm getting 0.7161, which is 71.61%. All right. Using the normal model, 650-50. Again, this is your mean. This is your standard deviation. What percent of scores fall between 700 and 725? So again, for both of these, I would need to turn them into z-scores as my step 1. So z equals the observation, which is 700, minus the mean, which is 650, divided by the standard deviation. And that's going to give you 1. And then we would do it again and say 725 minus 650 divided by 50. And that's going to give you 1.5. All right, 75 divided by 50 is going to be 1.5. So what that's effectively saying is you've got your curve here. All right, if this is 0, we're saying from 1 to 1.5, what part of that curve, what area does that shading correspond to? So again, on this one, we should be expecting an answer that's not all that large. All right, so NCDF from 1 to 1.5 when our mean is 0, when our standard deviation is 1. All right, so again, these don't always have to be negative 999s and positive 999s. This time our lower bound is 1, our upper bound is 1.5, mean and standard deviation. So we do get a pretty small answer there of 0.0918. 0.0918, which is also 9.18%. All right, what z-score represents the 25th percentile? All right, so again, 25th percentile would mean the bottom 25%. So we're telling you, okay, there's 25% of the curve shaded. What z-score does that correspond to? All right, so this is going back to our inverse norm. This time we're doing 0.25, 0, 1. All right, so we can go to our distribution. We can go to inverse norm, 0.25, 0, 1. And we get a z-score of negative 0.6745. And again, this one does not get turned to a percentage because it is a z-score. So that's just negative 0.6745 standard deviations below the mean. All right, using an n of 75,8, where the 75 is the mean and the 8 is the standard deviation, the highest 10% of the class scored above what value? So just a reminder here that if you're looking for the highest 10% and you're trying to figure out what value that was, so if this is 10%, that means that 90% of the curve is to the left. And that's important because inverse norm only goes down. So if we want to know the highest 10%, we actually have to use inverse norm of 90%. So we could say inverse norm of 0.90 when the mean is 0 and the standard deviation is 1. All right. So 0.9 mean 0, standard deviation 1. That gives us a z-score of 1.2816. All right, this right here is my z-score. Now, it wants to know the actual value, all right? They want to know what value it is. So I have to take this z-score and turn it back into its actual value. So to do that, I say, all right, my z-score formula is the observation minus the mean divided by the standard deviation. I know my z-score. I don't know the observation yet. That's what I'm solving for. I know my mean, it's 75. I know my standard deviation, it's 8. So then it's just a matter of solving that simple equation. So 1.2816 times 8, because you're going to multiply both sides of the equation by 8. And then you're going to add 75 to both sides of the equation, and you're going to end up with x equals 85.2528. All right, so that would be your final answer, which is basically saying the highest 10% of the class scored above an 85. All right. So let's take a look at the back now, where we move into the world of sort of like word problems and applying this to a situation. All right, so here we have a lid manufacturer. I figured, what is more exciting than manufacturing lids for disposable cups? So that was like the first problem that I chose to use so that I would catch your interest and just not let go. So basically what we have here is large drink cups require lids with a diameter between 3.95 and 4.05. The restaurant's lid supplier claims the diameter of their large lids follows a normal distribution with 3.98 and a standard deviation of 0.02. Now, quick aside here is normal distributions get used in manufacturing all the time because you can have certain specifications for how you're going to build something, but there's always going to be slight variations. All right, most of them are going to end up really close to the specifications, but you're going to have some that end up too big and some that end up too small. All right, now you're probably going to have quite a bit that are just a little too big and quite a bit that are just a little too small. And then as you get further away from those specifications, less and less are likely to exist. Like you're probably not going to find a lid that's 4.2 inches. You're probably not going to find a lid that's 3.6 inches. So we can see that it's going to follow sort of that normal distribution curve where most of them are going to be right at the specifications. You'll still have quite a bit that are a little low and a little high, but as you get further away, the amount that really got messed up are going to be few and far between. So the first question says, what percent of lids are too small to fit? So that's basically saying what percent are less than 3.95. All right, because we know that 3.95 is the smallest size that will fit. All right, so we're going to start by turning 3.95 into a z-score. So we'll say, all right, z equals 3.95 minus the mean of 3.98 divided by the standard deviation of 0.02. All right. And then when we work that out, we're just going to get a z-score of negative 1.5. All right. So if we draw our little picture here, we're basically saying, all right, you've got a z-score of negative 1.5. What percent of the curve does that work out to be? All right. So we'll do it the same way we've been doing all the other ones. NCDF from negative 9999 to negative 1.5 when the mean is 0 and the standard deviation is 1. All right. So NCDF, negative 9999, negative 1.5, mean 0, standard deviation 1. And we can see that it works out to be like 6.68%, so 0.0668, which works out to be 6.68%. Okay. What percent of lids are too big to fit? All right. So basically, this is asking what percent are above 4.05. All right. So we're going to do the same exact thing. We're going to say z equals 4.05 minus 3.98 divided by 0.02. All right. So this is going to give us a pretty large z-score. And we're going to see that it works out to be 3.5, which is 3.5 standard deviations above the mean. So if we look at our curve here, we're talking just about this tiny little bit over here on the right. So when we do our NCDF, we should expect to get a really small answer. So NCDF from 3.5 to 9999 when the mean is 0, the standard deviation is 1. So 3.5 comma 9999, mean is 0, standard deviation is 1. Right? And we do get a really tiny answer because you have to notice there we have that e to the negative fourth. So that means that we're actually 0.0002327. All right. Or as a percent, 0.02327%. All right, so a really tiny number there. And if you think about this from a business point of view, this actually makes a lot of sense. If you're quoting out your lids, you're more likely to want lids that are too small. Because if somebody picks up a lid that's too small and they put it on and try to put it on, it's not going to fit. And they're going to be like, oh, that's annoying. And they're going to grab a new lid. If somebody puts on a lid that's too big, they might not realize that it's too big. They might take the drink. They may try to drink from the drink, or they might put the drink in their car. And then if it spills, it either spills on them because the lid pops off, or it spills all over the car because you hit a bump and the lid pops off. And people are going to be really annoyed by that. They're not going to be that annoyed by a lid that's too small. They're going to be like, all right, let me just grab another lid. But lids that are too big potentially have really negative consequences. So if you're the manufacturer, you can use this information to make sure that, like, okay, we're willing to have more that are too small as long as we have a very tiny amount that end up too big, because too big is a much larger problem for us than too small. Now, again, this is sort of a dull example, but this sort of thing happens all of the time in manufacturing and production and all these other things. When you're setting your specifications and when you're designing the machines, you design it in such a way that you sort of allow mistakes in the direction that it's not going to cause a big problem, and be really careful to avoid mistakes in the direction that could cause major problems. All right, so let's read on here. The supplier is considering two changes to reduce the percent of its large cup lids that are too small to less than 1%. All right, so they're saying, oh, this 6% is too high. We need to cut that down because we're throwing away too many lids. One strategy is to adjust the mean diameter of its lids. So basically telling the manufacturer, hey, adjust your machine so that instead of the mean being 3.98, it's 3.95 or whatever. Another option is to alter the production process, thereby decreasing the standard deviation of the lid diameters. So how do you do that? Well, standard deviation is kind of basically when the machine doesn't do exactly what it's supposed to do. So if you perform maintenance on the machine more frequently, if you get better materials, if you buy a new machine, it's possible that you might be able to reduce this standard deviation. So changing the mean is usually pretty simple. It's just changing the settings on the machine. Reducing the standard deviation can actually be a lot more difficult because then you're looking at like your whole production process and what you can do to improve your production process so that you don't have that same variation in results, and you're getting more consistent results time in and time out. All right, so that's just my little aside there. Let's actually look at the problem here. If the standard deviation stayed the same, what mean value should the supplier set to ensure that less than 1% of their lids are too small to fit? What z-score corresponds to the first percentile? All right, so basically we're trying to find the value at which only 1% of this curve is going to be shaded. All right, so to do that, we're going to use inverse norm. So we'll start with inverse norm of 0.01 when the mean is 0 and the standard deviation is 1. All right, so inverse norm of 0.01, mean of 0, standard deviation of 1. And we get negative 2.3263. All right, so this is my z-score. All right, so that's my z-score. Now, if I think about the z-score formula, it's z equals observation minus mean divided by standard deviation. Now, I know my z-score. That's negative 2.3263. All right, it told me the standard deviation was staying the same, so I know that's still 0.02. I'm trying to figure out what the mean is, all right, what I need to set my mean to. So that's going to be my x. Now the question is, what is my observation? Well, the observation is the size at which the lid is too small, all right, because that's what we're testing here. So that would be our 3.95. So the 3.95, which we got from the problem, is our observation. We're figuring out what mean that has to correspond to, and then all of this rest stayed the same. So at this point, you just have to solve this equation. So you've got negative 2.3263. All right, sorry, negative 2.3263. I'm going to multiply both sides by 0.02. All right, that gives me 3.95 minus x equals this. All right, so I can basically what I'm going to, here, let me just write it out. So I've got this right now of negative 0.046526 equals 3.95 minus x. So you could solve this a couple of ways. You could subtract 3.95 from both sides, then you'd have a negative x, so you'd have to divide by -1. You could add x to both sides and then add this over to the other side. It doesn't really matter how you do it. On the calculator, I'm just going to subtract 3.95, and then I'm going to divide both sides by -1. So that tells me right there that my machine would have to be set to 3.996526. And if I set my machine to that value, I would only end up with 1% of my lids too small to fit. So I'd end up with 1% of my lids under 3.95. Basically, if I redid this problem, but instead of using 3.98, I use 3.996526, the answer would be 1%. All right, that's what we just did in this problem. We said, all right, what percent are less than 3.95? But instead of using the mean and standard deviation from the problem, we use this new mean. I could tell you the answer would be 1%. It wouldn't be this 6% anymore. It would go down to 1%. Now, this second part is asking the same question, but it's saying, instead of changing the mean, let's change the standard deviation. So everything else stays the same. We're still looking for the z-score at 1%, which means we're doing the same exact inverse norm, which means we're going to get the same exact z-score. All right, all of that's the same. We're still using the same exact z-score formula because there is no other formula, observation minus mean divided by standard deviation. The only difference is we're solving for something different. All right, so we still know our z, 0.23263. We still know our observation because it's the size at which the lid is too small. This time we're keeping the mean the same, so 3.98, that's coming from the problem. And instead we're solving for the standard deviation. All right, so, to solve this, you'd multiply both sides by x and get minus 2.3263x equals, and then we could combine the like terms there and get negative 0.03. And then you just have to divide both sides by that. So let me do that quick. 3.95 minus 3.98 divided by negative 2.3263. All right, and you end up with an x, or a standard deviation, of 0.01, we'll say 29. All right, so this is your new standard deviation. So again, this one was a standard deviation. This one up here was a mean. All right, and again, what this is saying is if you redid this problem up here and kept the mean at 3.98, but changed the standard deviation to 0.0129, you would end up with an answer of 1% instead of 6.68%. All right, that's what we were trying to accomplish with this problem here. All right, and I can prove it to you really quick. Let me just do it all on the calculator. So if I do 3.95 minus 3.98, and now I divide by my new standard deviation of 0.0129, I get a z-score of negative 2.32558. So let's just say negative 3.256. So if I go to my normal distribution, and I go from negative 999 to negative 356? Whoops. 3256. Negative 999 to negative 2.3256. When the mean is 0 and the standard deviation is 1, I'm going to get an answer of 1%. Again, it's a little different because of rounding, but that's what these problems are actually accomplishing. All right, they're going through and they're figuring out, all right, what would the mean and the standard deviation have to be to get an answer of 1% to this original problem? All right, so again, I hope this was helpful. I hope it showed you some of the different ways you can use standard deviation. And again, normal distribution, standard deviation, mean. And if you have any questions, feel free to reach out. All right, have a great day.